A very good morning to all of you. So I cordially welcome you all for this important course on the applied thermodynamics. So in the today's class, we are able to discuss about the problems on Rankine cycle and similarly the how can you represent the modified Rankine cycle and what is its importance. So the motivation of this particular lecture is it is very essential to know the working principle of a modified Rankine cycle and similarly how can we represent the same modified Rankine cycle on the PV diagram and TS diagrams to calculate the performance of a thermal power plant. And similarly, the lecture outcome after completion of this particular lecture, you should be in a position to solve the problems on Rankine cycle and represent modified Rankine cycle on PV as well as on TS diagram. So in the last class, I've already discussed about the Rankine cycle importance and how can you represent the Rankine cycle on PV diagram as well as on the TS diagram. So just you go through the lecture once again. So those who missed that particular lecture, once again, just you go through that important one. That is a Rankine cycle. So based on the previous class notes only, we are able to solve some important problems on the Rankine cycle. So now let us go to the first important problem. So in a Rankine cycle, the steam at inlet to a turbine is dry saturated at a pressure of 35 bar and the exhaust pressure is the 0.2 bar. So he has given the initial condition of the pressure as the dry saturated and the exhaust pressure is the 0.2 bar and he is asking us to calculate the four important parameters. So first of all, you write down the bar convert into the Newton per meter square or the pascals and similarly it is condenser pressure is also equivalent to 0.2 bar. So mass flow rate of the steam is given as 9.5 kgs per second. So now is asking us to find out the four important parameters, that is the pump work, turbine work, Rankine efficiency and condenser heat flow. So go to the steam tables or go to the Molière chart and at a dry saturated steam P1 is equal to 3500 kilopascals. What are the values of H1 and S1? Note it down. So here because he clearly mentioned that the point one it is a dry saturated steam. So locate point number one. So that is a 35 bar. So 35 bar line wherever it is meeting the saturated line. So that is my point number one. So from point number one draw a horizontal line. So this is equivalent to H1. And similarly it is the isentropic expansion process is taking place 1 to 2. So draw a vertical line wherever it is intersecting P2 is equivalent to 0.2 bar. So this is my point number two. So find it out what is the value of the H2 and similarly you also find it out what is the value of the S1 is equivalent to S2 and similarly here also S3 is equivalent to S4 and find it out H3 value as well as the H4 values from the Molière chart as well as from the steam tables. So here the x value we find it out as 0.7476 that is here. So point number 2. So what is the dryness fraction value is passing through this particular point number 2. So it is equivalent to 0.75 or 7476. So x2 is equivalent to approximately 0.75. That is the inlet condition is given as the dry steam and now the exit condition is basically it is the wet steam because the dryness fraction value is lesser than 1, so we are able to say that it is the wet steam. So once you find out the exit condition is equivalent to the wet steam, then you find out the enthalpy value at the exit. So that is formula H2 is equivalent to HF2 plus X into HFG2. The corresponding pressure is 0.2 bar, that is nothing but the 20 kilopascals. So find it as H2. And always we know that pump work is always equal to Vf into P1 minus P2. So substitute what is the value of the Vf, that is here you can see the Vf value 20 kilopascals from the steam tables we are able to find it as Vf. So P1 P2 values are already known to you. So find out Wp and H4 is equivalent to H3 plus Wp. So find out H4 is equivalent to so and so. Now similarly, the pump work required, so mass flow rate of the steam, it is a 9.5 kgs per second. So substitute here, we are able to get pump work is equal to so and so. Turbine work, because 1 to 2 process is taking place in the turbine. So m dot S into H1 minus H2. So it is my turbine work. Net power is always equivalent to turbine work minus pump work. So this will be equivalent to 7448.95 kilowatts. So total heat supplied to the steam. So that is the boiler. So boiler is basically represented by 124. It is taking place in the boiler. So Qin is equivalent to m dot S into H1 minus H4. So it is the Qin. And you know that the Rankine cycle efficiency is nothing but net work done divided by the heat input. Substitute the values, we are able to get the Rankine cycle efficiency is equivalent to 30.78 percentage. And the condenser heat flow, that is the condenser process is taking place in the 2 to 3 according to the constant pressure process. Substitute the values of the H2 and H3. Find it out condenser heat flow as 16,750.6 kilowatts. And similarly, you can solve the another problem, that is the steam enters the turbine as 100% saturated vapor. That is, the inlet condition is given as 100% saturated vapor, and saturated liquid enters the pump at a pressure of so and so. So he is asking us to calculate all these particular the 5 parameters. So first of all, write down the given condition of the P1, and the condenser exit is given, and heat rate to the boiler is also given. And go to the steam tables and go to the Molière chart and write down the properties at point number 1, point number 2, point number 3 as well as the point number 4. So in the state number 1, we are able to have P1 is equivalent to 6 megapascals, so convert into the kilopascals. And what is the value of the H1 and S1? We are able to get it from the steam tables. And similarly, at the state number 2, also you calculate all these particular the property values, state number 3, and similarly at the state number 4. So now initially you find out, so whether what is the value of the X after expansion, that is the exit condition, we don't know, because inlet condition is given as the dry steam, but the exit condition we have to find out. So for this particular purpose, we have to find out what is the value of the dryness fraction. So here it is lesser than 1. So that's why we are able to say that exit condition is equivalent to wet steam. So substitute in the respective formulas in the similar to the previous problem. Find out H2, find out WP, and similarly here find out the turbine work, and similarly the net work, and then heat input. So find out the thermal efficiency and the mass flow rate, exactly similar to the previous problem. So it is a net work, that is the power developed by the cycle, work ratio. So here the work ratio is nothing but net work produced by the turbine work. Specific steam consumption 3600 by W net. You know all these particular formulas from the first slide. So now you simply substitute, you find out all these particular the answers. Then the second important topic in the today's CDT is the modified Rankine cycle. So here in the modified Rankine cycles are basically used in the steam engines. So far we are discussing about the steam turbines. So this particular paragraph is very important one. So that is, just you go to the indicator diagram. So in this particular indicator diagram, that is normally in the Rankine cycle, we are expanding up to this particular 2 to 2 dash. So this is possible in the Rankine cycle, but in the modified Rankine cycle, we are not expanding up to the toe. That is, we are not expanding up to this particular one. We are restricting to point number 2 only. So from the point number 2 only, we are compressing in the pump. So that's why this is the only difference we are able to observe from the Rankine cycle to the modified Rankine cycle. Just you can see. So this much amount of this is called as the toe portion. This is amount of the toe portion is basically lost. So go to the just previous slide here. The expansion of the steam is not taken to toe of the curve, the back pressure, or else the stroke of the engine will be very long, but the work obtained in this part is very small. Thus the length of the stroke reduces without appreciable reduction in the power output of the engine. So it is the modification in the Rankine cycle used for the steam engines. So that is the difference between the Rankine cycle and the modified the Rankine cycle. So here the efficiency of the modified Rankine cycle, so it's going to be calculated by using this particular formula. It is exactly similar to this particular Rankine cycle. The only change you are able to observe here. So based on this particular the input, now you should be in a position to solve some important questions which are given in the previous GATE and IES examination. So let us consider the first question. For two cycles coupled in series, the topping cycle has an efficiency of the 30% and the bottoming cycle has an efficiency of the 20%. then how can we calculate the overall combined cycle efficiency? So that is, we know that N2, that is the combined cycle N2 will be equivalent to, so that is overall combined cycle N1 plus N2 minus N1 into N2. That is the same formula here I have written. So 1 minus N, that is the N is equivalent to N1 plus N2 into minus N1 into N2. This is the formula by which you are able to find out the overall combined cycle efficiency. So you know N1 value, you know N2 value, substitute here, you are able to get 44%. So that's why the answer is B. So similarly, go to the next problem. A steam plant has a boiler efficiency of the 92%, turbine efficiency, generator efficiency, and the cycle efficiency. If the 6% of the generated power is used to run the auxiliaries, the overall plant efficiency is, so it is asked in the gate 1996. So the formula is very, very important one. So the overall efficiency is equivalent to boiler efficiency into turbine efficiency into generator efficiency into auxiliary efficiency. So from which we are able to calculate, so that is the overall efficiency will be equivalent to, it is a 0.34 or it is also equivalent to is a 94%. So the answer, the 34%, sorry, not 94. So the answer is equivalent to A. So like this, we are able to solve some important problems on the Rankine cycle, and similarly, how can we represent the modified Rankine cycle on the PV diagram as well as on the TS diagram? What is the difference between the Rankine cycle and modified Rankine cycle? So these are the things which we discussed in the today's class. So thank you one and all for listening this lecture on this important topic.